This tension test experiment will cover steel, aluminum, and copper. We have a shot of the load cell here that we're using for the experiment. It has a capacity of about 30 kilonewtons. So in our lab we have two types of plates that we can use within the grips. These are a triangular type plate that we can use for circular type samples, and it'll be the plate type that we use for this experiment. We also have a set of flat plates that can be used with more rectangular type samples, which can be seen here. Additionally, the program we'll use will be called TWE Elite. We have some built-in tension test experiments that we can use for our test. So once the program opens, we'll want to open our tension test experiment. So we can go to File, Open Test, and then we'll want our tension test experiment. So there are several types of tension tests in our computer software, so we're using the one called New Tension Test today, and the only difference in that one and some of the other tension test experiments in our setup is the New Tension Test experiment can reach a higher maximum load than some of the other tension tests. So you'll see the bottom section of our software, it gives us load, crosshead, and extensometer, and then our time step as our test proceeds. And then our extensometer that will be used to help us calculate our strain measurement for our stress strain curve can be seen here. It has a 1-inch gauge length between each of those knife edges, so the knife edges are exactly 1 inch apart. It has some built-in springs, so then as the sample moves, it will move with that, and then that'll be able to calculate our change in length from our original state. So closed, you can see those knife edges that are exactly 1 inch apart. So first will be our steel experiment. So we have our circular type steel specimen here, and we'll take this and place one end into the clamped section of our test system, and if the specimen doesn't fit, we just kind of widen the test grips in order to create more space. So we're just creating some more space vertically for this sample so it'll fit better, and you'll see that it can go all the way to the bottom plate. So we want that top section of our grip to hold the bottom section of our specimen, so we're just going to kind of slightly raise that specimen so we can tighten the grip around that base of the specimen. So you can see here that movement to tighten the grip around that bottom of the specimen. So next we can zero out our load, crosshead, and extensometer, and this will give us a starting point for our original test. So now we can measure the center of our specimen to get our initial cross-section dimension, or diameter. So you'll see that our caliper set is set to 0. So we will measure the dimension of this center section of the specimen and use that for our area measurement of our specimen. So this measurement's also in inches. So now we want to place the extensometer onto our sample. So we'll move the spring clamps out of the way, and we'll take the edges of the extensometer and put it against the side of the center of the steel specimen, and then we will adjust our springs to grasp around the section. So we want to make sure that those springs are in the center, and then we'll take a marking utensil or a Sharpie and mark at the original 1-inch gauge length separation for our sample, and that'll give us a starting point for our original 1-inch gauge length. Once the test is completed, we can look at the distance between those two markings, and that'll be the difference between essentially the lengthening of our specimen. So we'll go ahead and zero these out again. Since we used the extensometer as part of the demonstration, we want to make sure that that's set to 0 before we start. And now we're going to lower the top section of our clamps onto the top section of the specimen in order to tighten the grip on the top of our specimen to run our test. So we can more quickly lower it until we get to kind of the edges of our clamp, and then we want to slowly lower the top clamp onto the top section of the specimen. Make sure that it'll clear that path for the actual grips, and then once we know that there's no kind of contact in that specimen, we can kind of lower it a little bit more in order to be able to actually grip it tightly on it. So now we have the top part of the specimen loaded, so now we can tighten the top section. So you can also use your hand to stabilize the top section of the clamp so there's no like twisting added additionally onto the specimen. And you'll see that we have a preload of around 201 pounds on this test. So we don't want to zero that out again because that's real load already on the specimen that we've used. And if we take that load away, then we won't have our correct amount of load when we finish the test. So now we can run our test or start our test in terms of playing the computer system running the load dimension aspect of our vertical 1D dimensional test. So a little more than halfway through our test, once we get to kind of the ultimate strength region of our test, we'll get a notification that the extensometer needs to be removed. And we don't want the specimen to fracture with the extensometer on it. They're fairly sensitive pieces of equipment, so we want to remove it before the specimen actually fractures. So we want to carefully remove the extensometer and place it to the side, and then once the test has been paused, we remove it, and then we can resume the test. So at this point, the strain data will no longer be valid because the extensometer has been removed. So now we have fracture of our specimen, and since the strain data is not valid because there was nothing measuring that change in length anymore, we can adjust for that in our data when we make our stress strain curve. But the force data is valid because the computer is still measuring the amount of load that is being added to the specimen until fracture occurs. So now we can raise the top grip on the test specimen, loosen the grips, and remove each end of the specimen in order to find our final gauge length, which is the final distance between each of those Sharpie markings for where the knife edges essentially ended from our starting point, and then we'll also measure the cross-sectional diameter at the fracture point, and that will be our final cross-section diameter. So here we're measuring our final gauge length, and we'll use the calipers to measure the distance between those indentation markings. So now we're doing the aluminum sample. The process is essentially the same for steel, aluminum, and copper. So this shows the end of the aluminum sample previously, so now we'll be doing the copper sample. Again, the process is generally the same. So now we'll export the data. So in order to export our raw data for our experiment for the metals that we test, we go to File, Export, and Raw Data. We'll select the test run that we want to export. In this case, we'll export test 88. In that case, it was our copper specimen we just ran. You can save it to a location of interest on the specimen, and it prints out as a text file in that location for the load, crosshead, x-sensometer, and time step. And then you can load this into an Excel document, use different graphing software programs, or analyze the data that you obtain.